Hello, listeners. Welcome back to Hafi's Sleep. Sit back, get comfortable. Let's take a little journey together. A journey into one of the most fantastical, seemingly science fiction ideas that just so happens to be absolutely true. We're going to talk about a mirror world, a kind of cosmic photo negative, a substance so strange that its very existence seems to defy logic. We're going to talk about antimatter. Now, I know what you might be thinking. Antimatter? Isn't that the stuff that powers the Starship Enterprise? The impossibly volatile fuel that lets Captain Picard warp across the galaxy? Well, yes, it is that. But it is also so much more. It is a real, tangible, and profoundly important part of our universe. It's not science fiction, it's science fact. But here's the million-dollar question, the one we're going to answer together over our little chat. How on earth do we know that? How can we be so sure that this ghostly, elusive counterpart to everything we see and touch and are made of actually exists? If it's all around us, why don't we see it? Why hasn't it blown us all to smithereens? The story of how we discovered antimatter, and how we continue to prove its existence every single day, is a detective story. It's a cosmic whodunit, filled with brilliant minds, ingenious experiments, and predictions so precise they border on the prophetic. It's a tale that begins not in a far-off galaxy, but in the quiet confines of a theorist's mind, with a piece of chalk and a blackboard. So, let's start at the very beginning. It's a very good place to start. Our story truly kicks off in the late 1920s. The world of physics was buzzing. The physics community is absolutely electrified, buzzing with the crazy, wonderful, and utterly mind-bending ideas of quantum mechanics. It's as if scientists had been trying to describe a beautiful, complex symphony using only a single drum beat for centuries, and suddenly, someone handed them the sheet music for the entire orchestra. They could finally hear the strings, the woodwinds, the brass, the full, rich, and often bizarre harmony of the subatomic world. This new quantum theory was the work of giants. Erwin Schrödinger gave us an equation that describes not a particle, but a wave of probability, a cloud of maybe, telling us where an electron is likely to be, but never exactly where it is until we look. It's a bit like knowing your lost keys are probably in the living room, but you can't be sure until you go in and search for them. And the very act of searching somehow changes where they were a moment ago. Werner Heisenberg then came along with his uncertainty principle, which basically says, there's a fundamental limit to what we can know. You can know an electron's speed very precisely, or its location very precisely, but never both at the exact same time. It's not a limitation of our microscopes, it's a built-in feature of the universe itself. And Niels Bohr, the great interpreter, helped make sense of it all, painting a picture of atoms where electrons live in specific quantized energy levels, like rungs on a ladder. They can't exist between rungs. They jump from one to another in a quantum leap. This new picture was incredibly powerful. It explained the behavior of atoms, the way they absorb and emit light, the very structure of the periodic table, with an accuracy that was nothing short of miraculous. But for all its brilliance, this new symphony had a problem. It was missing a crucial instrument. You see, this version of quantum mechanics was built for a relatively slow-paced world, the world of electrons orbiting an atom. Their speeds, while fast to us, are a tiny fraction of the speed of light. And this is where our old friend Albert Einstein comes waltzing back into the story. 2 decades earlier, he had turned the world on its head with his theory of special relativity. This theory dealt with the realm of the extremely fast. It said that as objects approach the speed of light, crazy things start to happen. Time itself begins to slow down for them relative to a stationary observer. Their length contracts in the direction of motion. Their mass effectively increases, making it harder and harder to push them any faster. It's a world where nothing is absolute except the speed of light itself. If you were on a train moving at 90% the speed of light and you turned on a flashlight, the beam of light would still rush away from you at exactly 186,282 miles per second, not one bit more. Not exactly common sense, but proven true time and time again. Now, here was the conflict. Schrödinger's beautiful equation was thoroughly non-relativistic. It treated space and time as separate, absolute entities, just as Newton had. It completely ignored Einstein's revolutionary discovery that space and time are woven together into a single fabric called space-time. This meant that while the equation was perfect for describing the lazy, meandering electron in a hydrogen atom, it was utterly useless for describing an electron screaming along in a particle accelerator at 99.9999% the speed of light, or an electron caught in the immense gravitational pull of a neutron star, where relativity's effects are paramount. It was like having the world's most perfect, detailed rulebook for playing checkers, but then being asked to play a game of three-dimensional chess in zero gravity. The basic concepts of moving pieces might be similar, but the old rules simply don't apply in this new, more extreme environment. Physicists had two rule books for the universe, one for the very small, quantum mechanics, and one for the very fast, relativity. And the two rule books were written in completely different languages. They couldn't talk to each other. This was more than just a theoretical annoyance. It was a glaring hole in their understanding. It was an itch that the finest minds in physics were desperate to scratch. They needed a new theory, a unified equation that could describe the quantum behavior of a particle like an electron, while also respecting the cosmic speed limit and weird space-time rules of Einstein's relativity. They needed a quantum theory that was relativistic. The task was monumental. It required a mind that could think in the abstract language of higher mathematics and yet be guided by a deep intuition about physical reality. It required someone who could see the harmony hidden within the apparent discord, and that someone was a quiet, intensely focused young British physicist named Paul Maurice Dirac. Dirac was a legendarily peculiar and precise man. He spoke only when absolutely necessary, and his sentences were famously concise and literal. A story goes that at a party in Copenhagen, someone commented, "It's windy today." Dirac got up, left the room, walked to the door, opened it, looked out, came back, sat down and said, "Yes." For him, every statement had to be verified and perfectly accurate. This wasn't social awkwardness. It was a reflection of how his mind worked, with absolute logical rigor. He believed that nature itself was fundamentally mathematical and beautiful, and that the key to discovering its secrets was to find the most elegant mathematical equations. For him, mathematical beauty was not just a guide, it was a physical principle. And so, Dirac set himself to this Herculean task, to take the Schrödinger equation and perform a radical surgery on it, to graft Einstein's relativity onto its heart. He wasn't just tinkering, he was trying to rebuild the engine of a car while it was running and turn it into a rocket ship. The problem was devilishly tricky. The original Schrödinger equation deals with quantities that are simple numbers. The energy of a particle, its momentum. But in Einstein's world, energy and momentum are woven together into a four-dimensional tapestry. To make things relativistic, Dirac had to find a way to treat them on equal footing. He struggled and wrestled with the mathematics for months. His breakthrough was as radical as it was brilliant. He realized that to make the equation work, the quantities he was dealing with couldn't be ordinary numbers. They had to be something more complex, mathematical objects called matrices. Without getting too deep into the weeds, think of it this way. Ordinary numbers are like simple one-note instructions. Add 5. Matrices are more like a full sheet of music. They can contain multiple intertwined instructions all at once. They have richer, more complex properties. By using these matrices, Dirac was essentially building an equation with more depth, more components. It was as if the original Schrödinger equation could only describe a particle in a flat, two-dimensional world, and Dirac's new equation could suddenly describe it in the full glory of 3 dimensions, plus time. This mathematical structure allowed the equation to automatically account for the strange mixing of space and time that relativity demanded. After this intense period of work in 1928, he unveiled his masterpiece, the Dirac equation. And it was a thing of beauty. It was concise, elegant, and mathematically stunning. It made a series of spectacular, testable predictions. First, it perfectly described the electron's spin, a peculiar property where electrons behave as if they are tiny spinning tops, creating their own little magnetic field. Spin had been discovered experimentally, but it had been bolted onto the old quantum theory as an afterthought, a weird add-on with no fundamental explanation. In Dirac's equation, spin wasn't an add-on. It fell out naturally. It was an inevitable consequence of merging quantum mechanics with relativity. The equation told the electron it had to spin. That was a huge win. Second, it predicted the magnetic moment of the electron, exactly how it would interact with a magnetic field, with jaw-dropping precision. The number it calculated matched experimental results perfectly. This was like predicting the exact weight of a single specific snowflake in a blizzard. Physicists were in awe. It seemed Dirac had done the impossible. He had written down the equation for the electron. It was a complete, perfect description. But then, as we heard before, they noticed the ghost in the machine. This new, more complex equation, with its matrix-based foundations, didn't have just one solution. It was a quadratic equation, and like all quadratic equations, it had 2 solutions. The first solution was the one everyone celebrated. It described our familiar electron, with its negative charge, its specific mass, and its spin. It was the answer they'd been looking for. But the second solution was a mirror. It described a particle that had the exact same mass as the electron, the exact same spin, but with a positive electric charge. Every property was identical, except the charge was flipped. This was baffling. The only positively charged particle anyone knew was the proton, but the proton was a heavyweight champion, nearly 2,000 times more massive than the lightweight electron. This second solution was clearly not a proton. The equation was unambiguous. It was something new. Now, imagine the turmoil in Dirac's mind and in the physics community. He had created this magnificent equation to solve one problem, and in doing so, it had created an even bigger, stranger problem. It was predicting the existence of a particle that nobody had ever seen, that had no right to exist according to all known science. Most physicists initially thought it must be a mathematical artifact, a meaningless byproduct of the fancy new math. Perhaps it could be ignored. But Dirac, with his profound belief in mathematical beauty, couldn't just ignore it. If the equation had 2 solutions, He felt both must be physically meaningful. The universe, in his view, wouldn't be so inelegant as to have a redundant, useless solution in its most fundamental equations. So, what was this positive electron? At first, Dirac and everyone else tried to explain it away. Maybe it was the proton? But that made no sense. The proton is nearly 2,000 times heavier than an electron. The equation was very clear. This second particle had to have the exact same mass as the electron. It couldn't be the proton. The equation was insistent. For every particle that exists, it seemed to demand the existence of a perfect mirror image twin, an antiparticle with opposite charge. Dirac, trying to avoid this radical idea, proposed a wild theory called the Dirac sea. He suggested that what we think of as a vacuum isn't empty at all. Instead, it's an infinite dense sea of electrons, all occupying negative energy states. Normally, we can't see this sea. But, he theorized, if a photon with enough energy comes along, it can kick an electron out of this sea, leaving behind a hole. This hole, the absence of a negative charge in a sea of negativity, would behave exactly like a particle with a positive charge. He called this hole an anti-electron. To most physicists, this sounded, frankly, a bit crazy. An infinitely dense sea of invisible electrons, it was a cumbersome, awkward solution. But it was the only one Dirac had to explain the stubborn mathematics of his own equation. The physics community was deeply skeptical. The great Niels Bohr reportedly told Dirac, who was heading to a conference, "Don't talk about your crazy hole theory. It will ruin your reputation." The equation was brilliant, but its prediction seemed like a mathematical artifact, a ghost in the machine, something to be ignored or explained away. But the universe, as it often does, had other plans. While the theorists were arguing, the experimentalists were busy building tools to see deeper into the heart of matter than ever before. One of these tools was the cloud chamber, a beautiful and simple device invented by C.T.R. Wilson. A cloud chamber is essentially a sealed environment filled with a vapor, like water or alcohol, that is just on the brink of condensing. When a charged particle zips through this chamber, it ionizes the atoms along its path, leaving a trail of charged particles in its wake. These charged particles act as nucleation points, causing the vapor to condense into tiny droplets around them. The result? You see a beautiful, thin fog trail, a visible path showing exactly where the particle has traveled. It's like seeing the contrail of a high-flying jet, but for subatomic particles. By placing the cloud chamber in a magnetic field, you can learn even more. A magnetic field will bend the path of a charged particle. The direction of the bend tells you whether the particle's charge is positive or negative, and the tightness of the curve tells you about its momentum. It was the particle tracker of its day. So, we left off with Paul Dirac, a man of quiet intensity and towering mathematical genius, who had just handed the world an equation that was both a masterpiece and a monster. It described the electron with breathtaking perfection, but it also whispered a secret about a twin, a mirror image particle with a positive charge. To most physicists, this was a curious but probably meaningless quirk of the math, a ghost in the machine. But science, at its best, is a conversation between two types of people: the theorists who imagine the possibilities, and the experimentalists who go out and see if the universe is actually listening. And, in a laboratory at Caltech, the universe was about to answer back, loudly and clearly. Enter Carl Anderson. If Dirac was the abstract dreamer, Anderson was the ultimate hands-on detective. He wasn't dealing with elegant equations on a blackboard. He was getting his hands dirty, building intricate machines to catch glimpses of the subatomic world. His specialty was cosmic rays. Now, that's a term we hear often, but let's really picture what they are. Imagine, right now, as you're listening to this, you are being gently showered by a constant, invisible rain. But this isn't water. It's a hail of particles from the deepest reaches of space. Protons, atomic nuclei, and other subatomic bits, accelerated to almost the speed of light by the unimaginable violence of supernovae, black holes, and other cosmic events. They are nature's own particle accelerator, bombarding our atmosphere 24/7, creating cascades of secondary particles that shower down upon us. Anderson's job was to be a detective at the scene of this eternal cosmic crime, looking for clues in the aftermath. His tool of choice was the cloud chamber, a device of such simple beauty it deserves its own moment in the spotlight. Invented by C.T.R. Wilson, it's a masterpiece of clever simplicity. Think of a cold glass of water on a hot day. The outside of the glass gets foggy with condensation. A cloud chamber works on a similar principle. It's a sealed container, typically with a glass top, filled with a vapor, like water or, more commonly, alcohol. The bottom of the chamber is cooled, often by dry ice, creating a steep temperature gradient. This makes the vapor inside incredibly supersaturated. It's desperate to condense into liquid droplets, but it needs something to condense around, a seed. Now enter our cosmic ray particle. When one of these high-speed subatomic bullets zips through the chamber, it doesn't just fly through empty space. It smashes into the atoms of the vapor inside. It's like a bowling ball screaming through a lane, not hitting the pins, but hitting the air molecules between the pins, knocking electrons loose from them. This process is called ionization. So, in its wake, the particle leaves a trail of charged debris, positive ions and free electrons. And here's the magic. These charged bits are perfect seeds for condensation. The supersaturated vapor instantly clings to them, forming millions of tiny liquid droplets. The result? A perfect visible fine fog trail that traces the exact path the particle took. It's like seeing the contrail of a jet high in the sky, but for something impossibly small. You are literally seeing the invisible. It's one of the most direct ways to see a subatomic particle. Anderson would set up a camera to take picture after picture of this chamber, hoping to capture these fleeting trails, these cosmic autographs. But Anderson was a particularly thorough detective. He didn't just have a cloud chamber, he supercharged it. He placed the entire chamber between the poles of a giant, powerful electromagnet. Why? Because a magnetic field is like a truth serum for charged particles. A charged particle moving through a magnetic field feels a force, a kind of sideways push that bends its path into a curve. The direction of the curve tells you the particle's charge. Remember the right-hand rule from physics class? A negatively charged electron will curve one way. A positively charged proton will curve the other. Furthermore, the tightness of the curve tells you about the particle's momentum. A high-energy, heavy particle barrels through with a gentle, lazy curve. A low-energy light particle gets thrown around in a tight, sharp circle. So now, from a single fog trail, Anderson could deduce 1. The particle's charge from the direction of the curve. 2. Its momentum from the tightness of the curve. And if you know the momentum, and you can make an educated guess about its speed, often close to light speed, you can get a sense of its mass. This was his detective's toolkit. But there was one more problem. Sometimes particles could come from below, from the Earth itself, or from the sides of the chamber. This could create confusion about the direction of travel. So, Anderson added a final stroke of genius. He inserted a thin plate of lead right through the middle of the cloud chamber. This lead plate was his master clue. Think of it as a speed bump on a road. When a particle hits this lead plate, it loses energy. It slows down. And because it slows down, its path bends more sharply after it exits the plate. It's like a car hitting a patch of mud. It goes in fast and straight and comes out slower and veers off more drastically. This was crucial. By comparing the curvature before and after the plate, Anderson could definitively determine the particle's direction of travel. The side with the gentler curve was before the plate, higher energy, faster speed. The side with the tighter curve was after the plate, lower energy, slower speed. The lead plate removed all ambiguity. It was an arrow of time for the particle's journey. Now, picture Anderson in his lab. It's 1932. He's developed thousands of photographs, each one a long shot, a cosmic lottery ticket. He's peering at these delicate, wispy trails, measuring their curves with painstaking precision. He's seen countless electrons, their negative charge making them curve in their characteristic way. He's seen protons, much heavier, with their positive charge, curving the opposite way but with a much lazier arc due to their mass. And then he sees it. A track that makes him stop. A trail that, at first glance, looks for all the world like an electron. It's thin and sharp, indicating a very light particle, just like an electron. But it's curving the wrong way. Under the influence of his magnet, it's bending in the direction that only a positively charged particle should bend. His mind must have raced through the possibilities. A proton? Impossible. A proton may have a positive charge, but it's a lumbering giant. To make such a sharp, tight curve, a proton would have to be moving impossibly slow, with almost no energy. It would have stopped dead in the chamber, not zipped through. The tightness of the curve screamed, lightweight particle, but the direction of the curve screamed, positive charge. It was a contradiction. It was like a detective finding a fingerprint at a crime scene that belonged to a known cat burglar, but the print was the size of a giant's. The evidence didn't fit any known suspect. His first thought, a natural one for a meticulous scientist, was that he was being fooled. Maybe it was just an ordinary electron, but it was coming up from the ground. If it were traveling upwards, the magnetic field would bend it in the opposite direction, making it look like a positive particle going downwards. It was a tricky illusion, but then he looked at the master clue, the lead plate. He measured the curvature on either side. The curve was gentler on top, tighter on the bottom. There was no doubt. The particle had lost energy going through the lead. It had come from above. It had entered the chamber from space, from the cosmos, hit the lead plate, slowed down, and continued downward. Its direction of travel was unequivocal, and with that direction confirmed, the curvature could mean only one thing. This was a particle from outer space, with the mass of an electron, but with a positive charge. He had found it. Dirac's ghost. The anti-electron. It was real. It wasn't a mathematical artifact. It wasn't a hole in an infinite sea. It was a tangible thing. A citizen of the universe, leaving its calling card in a cloud of alcohol vapor in a California lab. Anderson, true to his cautious and modest nature, didn't run through the halls shouting about confirming Dirac's theory. He simply, methodically, documented the evidence. He took more pictures. He found more examples. He built an ironclad case. And in his published paper, he gave it a simple, straightforward name: free of theoretical baggage. The positron, a handy portmanteau of positive electron. The impact was seismic. The physics world was, as we said, electrified. It's one thing for a theorist to predict something strange. It's another thing entirely for an experimentalist to hold it up and say, "Here it is." In an instant, Dirac's equation was transformed from a controversial, if brilliant, piece of math into a prophetic vision of reality. The positron's discovery was the ultimate validation of the power of theoretical physics. It showed that if the math is beautiful and self-consistent, even if it points to something seemingly impossible, we should trust it. The universe speaks in mathematics. The Nobel Prizes tell the story. Dirac was awarded his in 1933 for his theoretical work. The committee was essentially rewarding the prediction itself, even as the evidence was still being gathered and confirmed. And then, just 3 years later, in 1936, Anderson, along with Victor Hess, who discovered cosmic rays, was awarded the Nobel Prize for the experimental discovery. It's one of the swiftest recognitions in Nobel history, a testament to how profound and undeniable the discovery was. This moment, more than any other, is the bedrock of our knowledge of antimatter. It wasn't an inference or a deduction. It was a direct observation, a photograph. It was the universe holding up a sign for all to see. And it opened the floodgates. If the electron had an antiparticle, what else did? The discovery of the positron was the first crack in the dam, and a whole anti-world was waiting to burst through. It was the beginning of a new era, one where we stopped thinking of particles as solitary actors and started seeing them in pairs, in families, in a cosmic dance of matter and antimatter, forever linked by energy and annihilated by contact. And it all started with a quiet man, a clever machine, and a curious trail in the fog. Now, this was an incredible start. We had proof. A single specific antiparticle had been discovered. But this was just the beginning of the story. The positron was the key that unlocked a whole new world, or rather, a whole new anti-world. If the electron has an antiparticle, what about other particles? Does every single particle in the universe have a mirror twin? This became the next great question. Let's pause for a moment and think about what this really means. What is antimatter? We've established that it exists, but what are its properties? Well, the first and most obvious property is the opposite electric charge. A positron is identical to an electron in almost every single way, except it has a positive charge instead of a negative one. But is that the only difference? As physicists delved deeper, they discovered that the symmetry between matter and antimatter is far more profound and goes beyond just charge. Every particle has a set of quantum numbers that define its properties. Charge is 1. There's also lepton number. Electrons and their cousins, like muons and tau particles, are called leptons, and they have a lepton number of +1. Their antiparticles, like the positron, have a lepton number of 1. Similarly, quarks, the particles that make up protons and neutrons, have a baryon number of +1/3 for a single quark. So a proton, made of 3 quarks, has a baryon number of +1. Antiprotons have a baryon number of 1. There are other more subtle properties too, like strangeness or charm. And for each of these, the antiparticle has the opposite value. So, we've arrived at one of the most beautiful and then utterly mind-shattering ideas in all of physics. We've found the positron. We've found the antiproton. We're building anti-atoms. It seems like for every particle, there's an antiparticle, a perfect twin with opposite charge. It's a wonderfully symmetrical universe. It feels right. It feels elegant. And for a long time, physicists believed this symmetry wasn't just a cute coincidence. They believed it was absolute, woven into the very fabric of reality itself. They believed the universe was fundamentally impartial, that it didn't play favorites between matter and antimatter, or between left and right. This belief was enshrined in a principle called CP symmetry. Now that sounds like technical jargon, but let's unpack it, because understanding this is key to understanding one of the deepest mysteries of our existence. Let's break down this CP thing. C stands for charge conjugation. This is the simpler part. It's the swap we've been talking about. Imagine you have an experiment, say 2 electrons orbiting each other. Now you perform a C operation. You conjure a magic wand and poof! You replace every single particle with its antiparticle. So those 2 electrons become 2 positrons. Everything that was matter is now antimatter. That's charge conjugation. If the laws of physics are symmetric under C, then those 2 positrons should orbit each other in exactly the same way, with the same energies, the same distances, behaving in every single way identically to how the 2 electrons did. It should be impossible to tell from watching the dance, whether you're watching matter or antimatter. It's like changing all the actors in a play, but expecting every line, every movement, every emotion to be delivered exactly the same. Now, P stands for parity. This one is a bit more abstract, but also more fun. Parity is the idea of mirror symmetry. Imagine you're doing an experiment, and right next to it, you set up a perfect, gigantic mirror. You watch what happens in the real experiment, and you also watch what happens in the mirror. If the laws of physics obey parity symmetry, or P-symmetry, then the mirrored version of events should also be perfectly possible in the real world. The mirror image shouldn't look weird or impossible. It should look like a valid, real experiment that could be set up in a lab somewhere. Let's make this concrete. Think about a simple clockwise spinning top. You look at it in a mirror. What does it look like? It looks like it's spinning counterclockwise, right? Now, is there any law of physics that says a top can only spin clockwise? No, of course not. You can easily start a top spinning counterclockwise. The mirrored version is just as valid. The law of gravity works the same. Friction works the same. So for the spinning top, parity is conserved. The universe doesn't care about left or right in this case. For a long, long time, physicists just assumed this was true for everything. They assumed the universe was fundamentally ambidextrous. It was a deeply held article of faith. Why wouldn't it be? It seemed so obvious. The laws of physics are written in math, and math seems to be mirror invariant. There's no left-handed version of the number 7. So they extended this idea to the subatomic world. They believed that if you took, say, a radioactive nucleus that spat out an electron, and you looked at it in a mirror, the mirrored version, a nucleus spitting out an electron the other way, would be just as valid and would happen with exactly the same probability. It was thought to be an unbreakable law. Now here's the powerful part. Physicists combine these 2 ideas into CP symmetry. This is the big one. It says, if you take an experiment and you simultaneously do 2 things. 1. Swap every particle with its antiparticle, the C operation. 2. And look at the whole thing in a mirror, the P operation. Then the resulting CP transformed experiment should be utterly indistinguishable from the original. It should be exactly identical in every way. The laws of physics should not be able to tell the difference. Think of it like this. Imagine you have a strange, subatomic clock. It's made of matter, and its hands turn a certain way. Now you create its perfect mirror antimatter twin. You build a clock out of antimatter and put it in front of a mirror. CP symmetry says that this antimatter mirror clock will tick at exactly the same rate as your original matter clock. There would be no way to tell them apart. If CP symmetry holds, it means that matter and antimatter are not just twins. They are perfect, flawless mirror images of each other. The universe truly would have no preference. It would be the ultimate expression of cosmic fairness. This was the comfortable, elegant picture for decades. It was beautiful. It was tidy. It felt right. But then, in the mid-1950s, two brilliant physicists, Tsung-Dao Lee and Chen-Ning Yang, did something dangerous. They asked a simple question. They looked at this sacred cow of parity symmetry and asked, "Wait, has anyone actually checked if this is true for the weak nuclear force?" The weak nuclear force is one of the four fundamental forces of nature. It's the force responsible for a specific kind of radioactive decay. It's not as familiar as gravity or electromagnetism, but it's crucial for how the sun burns and how certain elements transform. What Li and Yang realized was that while everyone assumed parity was conserved for the weak force, no experiment had ever actually proven it. It was just taken for granted. They proposed a series of clever experiments that could actually test it. It was a bit like someone saying, "We all assume gravity works the same on Tuesday as it does on Monday. But has anyone ever actually dropped a ball on a Tuesday to check?" It was a breathtakingly bold question to ask. The task of actually doing this experiment fell to another legendary physicist, Chien-Shiung Wu, often called the First Lady of Physics. In 1956, she designed and conducted one of the most important and elegant experiments of the 20th century. She used atoms of cobalt-60, a radioactive isotope, and chilled them to near absolute zero to line them all up in the same direction using a magnetic field. These cobalt nuclei were like tiny spinning tops, all spinning in the same orientation. Due to the weak force, they decayed, spitting out electrons. Now, here's the key. If parity symmetry held, these electrons should be shot out equally in all directions. There should be no preference between up and down relative to the spin of the nuclei. It should be perfectly symmetrical. It would be like our spinning top earlier. The mirror image would be identical. But that's not what Madame Wu found. What she saw was stunning. The electrons were not emitted equally. They had an overwhelming preference. They were shooting out preferentially in one direction, opposite to the direction of the nuclear spins. It was fundamentally asymmetrical. Now, do the mirror operation. Imagine her experiment in a mirror. In the mirror, the spins of all the cobalt nuclei would be reversed. But the emission direction of the electrons would not reverse in the same way, because it's a mirror, left and right flip, but up and down don't. The result? The mirrored image would show electrons shooting out in the same direction as the nuclear spins. But this was a configuration that never happened in the real world. The mirror image was of an experiment that was impossible. This was monumental. It meant that the weak nuclear force could tell the difference between left and right. The universe, on a fundamental level, has a handedness. It has a favorite direction. It's not ambidextrous. It's left-handed, or right-handed, depending on your perspective. The point is, it cares. Parity was not conserved. The mirror universe would operate under different rules. This was like discovering that in a mirror, the reflection of a right hand is a right hand, not a left hand. It was that bizarre. The physics community was shocked. Li and Yang won the Nobel Prize with incredible speed the very next year, in 1957. Madame Wu, sadly, was not included, a fact many consider a great oversight. So parity was broken. The P in CP was flawed, but all was not lost. Perhaps the universe's sense of balance could be restored by combining it with charge conjugation. Maybe the universe's slight preference for, say, left-handed particles was perfectly balanced by a slight preference for right-handed antiparticles. Maybe the broken P symmetry and the broken C symmetry could cancel each other out, leaving the combined CP symmetry intact. It was a beautiful save. It meant that while the universe might be left-handed for matter, it would be right-handed for antimatter, maintaining an overall balance. The mirror antimatter clock would still tick the same way. This became the new hope. CP symmetry must be the true fundamental symmetry. For a few years, everyone breathed a sigh of relief. The universe was still elegant and balanced, just in a more subtle way. But the universe, it seems, loves to keep us on our toes. Just when we think we've figured out its rules, it throws us another curveball, and this one would be the biggest of all. So, we left off with the physics world in a state of relieved, if slightly wobbly, elegance. Madame Wu's experiment had shattered the naive idea that the universe was mirror-symmetric. It definitely had a favorite hand, a preference for left or right. But the brilliant save was to combine this broken mirror symmetry, parity, with the matter-antimatter swap, charge conjugation, into CP symmetry. The hope, the belief, was that while the universe might be left-handed for matter, it would be right-handed for antimatter, perfectly balancing the books. It was a beautiful idea. It meant the universe, deep down, was still fair. It didn't prefer matter over antimatter. It just expressed itself with a different handedness for each. If CP symmetry held, the mirror antimatter universe would still be perfectly identical to our own. This was the dogma. This was what everyone believed. And to test this new, more sophisticated symmetry, physicists turned to some of the strangest characters in the particle zoo, kaons. Now, kaons, also called K-mesons, are weird. They are profoundly, fundamentally weird, and their weirdness makes them perfect for probing the deepest symmetries of nature. So, let's get to know them a little. Kaons are particles that are created in high-energy collisions, like when cosmic rays smash into the atmosphere or in particle accelerators. But they're not stable. They don't hang around. They decay in a fraction of a second into other, more common particles, like pions, electrons, and neutrinos. But here's the first layer of their weirdness. They come in two types, with a peculiar property called strangeness. Don't you love that name? It's not just a cute label, it's an actual quantum number, like charge, that must be conserved in the strong and electromagnetic interactions. You have the K plus and its antiparticle, the K minus. But then you have the neutral kaons, the K0 and its antiparticle, the anti-K0. Now this is where it gets trippy. The K0 and the anti-K0 are distinct particles. They have opposite strangeness, but because of the quantum magic of the weak force, the same force that broke parity, they don't like to stay separate. They play a constant game of quantum identity theft. They mix together. It's as if you had two different paints, red and blue, but when you put them together, they don't make purple. They instead form two entirely new, stable colors that weren't in the original cans. Through this mixing, the neutral kaon system doesn't produce K0 and anti-K0 as we know them. Instead, it produces two entirely new composite particles, which physicists called K1 and K2, K long and K short. The K short is the introvert. It lives a very brief life, decaying away after about 9 billionths of a second. The K-long, K2, is the extrovert. It's much more stable, lasting nearly 600 times longer, a veritable eternity in the particle world. This difference in lifetime is huge and was a crucial clue. So, we left off with the physics world in a state of relieved, if slightly wobbly, elegance. Madame Wu's experiment had shattered the naive idea that the universe was mirror-symmetric. It definitely had a favorite hand, a preference for left or right. But the brilliant save was to combine this broken mirror symmetry, parity, with the matter-antimatter swap, charge conjugation, into CP symmetry. The hope, the belief, was that while the universe might be left-handed for matter, it would be right-handed for antimatter, perfectly balancing the books. It was a beautiful idea. It meant the universe, deep down, was still fair. It didn't prefer matter over antimatter. It just expressed itself with a different handedness for each. If CP symmetry held, the mirror antimatter universe would still be perfectly identical to our own. This was the dogma. This was what everyone believed. And to test this new, more sophisticated symmetry, physicists turned to some of the strangest characters in the particle zoo, kaons. Now, kaons, also called K-mesons, are weird. They are profoundly, fundamentally weird, and their weirdness makes them perfect for probing the deepest symmetries of nature. So let's get to know them a little. Kaons are particles that are created in high-energy collisions, like when cosmic rays smash into the atmosphere or in particle accelerators. But they're not stable. They don't hang around. They decay in a fraction of a second into other, more common particles, like pions, electrons, and neutrinos. But here's the first layer of their weirdness. They come in two types with a peculiar property called strangeness. Don't you love that name? It's not just a cute label. It's an actual quantum number, like charge, that must be conserved in the strong and electromagnetic interactions. You have the K plus and its antiparticle, the K. But then you have the neutral kaons, the K0 and its antiparticle, the anti-K0. Now this is where it gets trippy. The K0 and the anti-K0 are distinct particles. They have opposite strangeness. But because of the quantum magic of the weak force, the same force that broke parity, they don't like to stay separate. They play a constant game of quantum identity theft. They mix together. It's as if you had two different paints, red and blue. But when you put them together, they don't make purple. They instead form two entirely new, stable colors that weren't in the original cans. Through this mixing, the neutral kaon system doesn't produce K0 and anti-K0 as we know them. Instead, it produces two entirely new composite particles, which physicists called K1 and K2, K long and K short. The K short, K1, is the introvert. It lives a very brief life, decaying away after about 9 billionths of a second. The K long, K2, is the extrovert. It's much more stable, lasting nearly 600 times longer, a veritable eternity in the particle world. This difference in lifetime is huge and was a crucial clue. Now, enter James Cronin and Val Fitch. In 1964, they were working at the Brookhaven National Laboratory, studying these strange neutral kaons. Their experiment was a masterpiece of precision. They generated a beam of kaons. By the time this beam traveled several feet, the short-lived K-short particles would have all decayed away. What was left was a pure beam of only the long-lived K-long particles. According to the firmly believed CP symmetry, this beam of K-long particles should only have one allowed way to decay, into 3 pions. This was a calculated, definite prediction of CP symmetry. The decay into two pions was strictly forbidden for the K-long. It was against the law, the CP law. So Cronin and Fitch's mission was seemingly straightforward. Confirm that the long-lived chions dutifully decay into 3 pions and never into 2. They built an incredibly sensitive setup to detect the precise trajectories and energies of the particles coming from these decays. Their detectors were like the most meticulous courtroom stenographers, recording every detail of the final moments of these kaons. They spent months taking data, carefully analyzing the results, and then they saw it. Something impossible. Amidst the vast majority of 3 pion decays, there was a tiny, tiny signal. A few events, a mere handful out of thousands, where the K-long particle was defiantly, brazenly decaying into 2 pions. The first reaction, as with all great discoveries, was disbelief. It must be a mistake. It must be background noise. Perhaps a few of the short-lived K-short particles had somehow survived and contaminated the beam. They checked and rechecked. They examined their equipment for flaws. They searched for any possible error. But the signal persisted. It was real. It was small. Only about 1 in every 500 K-long decays broke the rule, but it was definitive. It was there. The implication was earth-shattering. This was not a small crack in the foundation. It was a chasm. If CP symmetry were perfect, this decay was absolutely forbidden. Its occurrence meant that CP symmetry was violated. The laws of physics were not perfectly symmetric between matter and antimatter. The universe, on a fundamental level, could tell the difference. The mirror antimatter universe would not behave exactly like ours. There is a tiny but real difference baked into the very heart of reality. Let's think about what this means in our clock analogy. Imagine you finally build your perfect antimatter clock and put it in front of a mirror. Before Cronin and Fitch, you'd expect the mirrored antimatter clock to tick at exactly the same rate as your original matter clock. But what they discovered was that if you watched for long enough, with sensitive enough equipment, you'd see that the antimatter mirror clock ticks very, very slightly slower. The difference is infinitesimal, but it's there. The 2 clocks are not identical. The universe has a tiny but measurable preference. This was a monumental discovery. It was so unexpected, so contrary to the established order, that when Cronin and Fitch first presented their results, the audience of physicists was largely silent, stunned. They knew they were witnessing something profound. For this discovery, Cronin and Fitch deservedly won the Nobel Prize in 1980. But why is this so important? Why does this tiny 1 in 500 violation matter so much? It matters because of the biggest question of all. Why are we here? Let's rewind to the Big Bang. The prevailing theory is that the universe began as an unimaginably hot, dense burst of pure energy, and according to Einstein's famous E=mc2, energy can convert into matter. But it can't just create matter. It must create matter and antimatter in equal, paired amounts. For every electron created, a positron must also be created. For every quark, an antiquark. The universe should have been born with perfectly symmetrical amounts of matter and antimatter. And then, within the first second of its life, all of those particle-antiparticle pairs should have found each other, annihilated in a spectacular flash of gamma rays, and turned back into pure energy. The entire universe should have ended right there. It should be a vast, empty expanse of light, with no atoms, no stars, no planets, and certainly no us. But we are here. You are listening to this. The galaxy is here. Everything we see is made of matter. So, something must have happened. something must have tipped the scales. For every billion matter-antimatter pairs that annihilated in the early universe, one single particle of matter must have been left over. That 1 in a billion surplus is what all the stars, planets, and people in the universe are made from. The question is, what caused that tipping? What process could possibly favor matter over antimatter by that tiny, crucial amount? The CP violation discovered by Cronin and Fitch is the only known phenomenon in all of physics that provides a mechanism for this. It proves that the laws of physics are not impartial. They do, in fact, treat matter and antimatter slightly differently. This tiny asymmetry, this slight preference encoded into the weak force, could be the reason we exist. There's a catch, though. The level of CP violation that Cronin and Fitch found in the kaon system is far, far too small to account for the vast matter-antimatter imbalance we see in the universe. It's like finding a single drop of water and knowing it must be part of a huge flood, but the drop is too small to explain the flood's size. So, the search was on. Was this a unique quirk of kaons, or was it a more universal principle? This question drives a huge amount of modern physics. It led to the Nobel Prize-winning discovery of CP violation in another family of particles, the B mesons, in the early 2000s. It is a central reason we built massive machines like the Large Hadron Collider at CERN to create billions of particles and antiparticles and watch them decay with exquisite precision, hunting for any other slight differences in their behavior. We are literally trying to find more pieces of the puzzle, to find a source of CP violation that is big enough to explain our existence. The work of Cronin and Fitch was a watershed moment. It transformed a philosophical question, why is there something rather than nothing, into a concrete experimental physics problem. It showed us that the universe is not quite as symmetrical as we thought, and that within that tiny imperfection might lie the reason for everything we see and everything we are. It's a humbling and thrilling thought that we are here because the universe, in its deepest laws, is just slightly, beautifully imperfect. But let's bring it back to our main question. How do we know? We know the positron exists because we saw its track in a cloud chamber. But what about other antiparticles? The next big target was the antiproton. Remember, the proton is nearly 2,000 times heavier than the electron. Creating one from energy requires, according to E=mc2, nearly 2,000 times more energy. You can't just wait for one to show up in cosmic rays. It's far too rare. To create antiprotons, you need to make them. You need to assemble enough pure energy in one place to conjure them into existence. This is where particle accelerators come in. These are the modern-day cloud chambers, but far more powerful. They are enormous machines, often miles long, that use powerful electromagnetic fields to accelerate particles, usually protons or electrons, to incredible speeds, getting them very, very close to the speed of light. This gives them a colossal amount of energy. We then smash these beams of particles into a target, or into another beam going the opposite direction. In the incredible violence of that collision, the kinetic energy of the particles is converted into mass, creating new particles. It's like smashing two watches together at unimaginable speeds, and not only breaking them into a million pieces, but having those pieces reassemble into new, more complex watches and clocks that weren't even in the original watches. It's pure alchemy, turning energy into matter. In 1955, Emilio Segre and Owen Chamberlain at the University of California, Berkeley, did exactly this. Using a particle accelerator called the Bevatron, which was specifically designed to have enough energy to create proton-antiproton pairs, they finally succeeded. They created antiprotons and crucially detected them. It wasn't easy. They were creating a mere handful of antiprotons amidst a raging storm of billions of other particles. Detecting them was like trying to find a single specific drop of water in a hurricane. But they did it, using sophisticated magnetic filters and timing measurements to identify the unique signature of the antiproton. Another Nobel Prize was awarded, this time in 1959. The antimatter family was growing. Soon after, the antineutron was discovered. This is particularly interesting because the neutron has no electric charge. So, if an antiparticle is defined by having opposite charge, what makes an antineutron different from a neutron? They are both neutral. The difference lies in other quantum numbers like baryon number. A neutron is made of 3 quarks, one up quark, charge +2/3, and 2 down quarks, charge -1/3 each, giving a total charge of 0. An antineutron is made of 3 antiquarks, 1 anti-up, charge -2/3, and 2 anti-down, charge +1/3 each. So, while the overall charge is still 0, its internal composition is the mirror image. When a neutron and an antineutron meet, they will still annihilate each other in a spectacular release of energy, proving they are indeed matter and antimatter counterparts. So now we have the whole anti-periodic table in a sense. We can make anti-atoms. We can take a positron, an anti-electron, and orbit it around an antiproton. What do you get? Anti-hydrogen, the simplest anti-atom. This is an incredible technical challenge. You can't just keep antimatter in a jar. The instant it touches the matter of the jar, it annihilates. So, how do you handle it? You use magnetic traps. Since many antiparticles are charged, like positrons and antiprotons, you can use powerful, complex magnetic fields to levitate them, suspending them in a perfect vacuum, away from any matter container walls. This is exactly what teams at CERN, like the Alpha collaboration, do. They create antiprotons and positrons, slow them down, and carefully coax them to combine into neutral antihydrogen atoms. But even though the atom is neutral overall, it has a tiny magnetic moment, like a little compass needle, which allows them to trap it with an intricate magnetic bottle. They have successfully trapped antihydrogen atoms for minutes, even hours at a time, and have begun to study them with exquisite precision. Why? To test, once again, that fundamental symmetry. Does antihydrogen absorb and emit light at exactly the same wavelengths as regular hydrogen? According to theory, it should. Any tiny difference would shake physics to its core. So far, within incredible precision, it seems to be identical. The symmetry holds, and this brings us to the most practical, everyday proof that antimatter exists. You might be interacting with it yourself today. If you or someone you know has ever had a PET scan in a hospital, you have directly benefited from antimatter. PET stands for positron emission tomography. Here's how it works. A patient is injected with a slightly radioactive tracer molecule, often a sugar molecule that is absorbed by cells. This tracer is chosen because it decays by emitting a positron. That's right. Inside a patient's body, tiny atoms are spitting out antimatter. This positron, the anti-electron, doesn't travel very far at all. Within a millimeter or two, it will inevitably meet an electron, its matter counterpart. They annihilate each other. The entire mass of both particles is converted into energy, specifically into 2 gamma-ray photons. And because of the conservation of momentum, these 2 photons fly away from the annihilation point in exactly opposite directions, 180 degrees apart. The PET scanner is a ring of detectors that surrounds the patient. It waits for this telltale signal. Two gamma rays hitting exactly opposite sides of the ring at exactly the same time. The scanner knows that the annihilation event must have occurred somewhere on the line between those two detection points. By detecting millions and millions of these events, a computer can triangulate the precise locations of all this activity and build up a stunningly detailed 3D image of metabolic activity inside the body. Cancer cells, which are often more metabolically active and absorb more of the tracer sugar, light up like Christmas trees on the scan. It is a life-saving technology built entirely on the reality of antimatter annihilation. It's not science fiction, it's medical reality. So, how do we know antimatter exists? We know because a brilliant theorist's equation demanded it. We know because a careful experimenter saw its track in a cloud chamber. We know because we create it by the particle in giant accelerators. And we can even assemble it into anti-atoms and hold them captive to study them. We know because its signature annihilation light is used to save lives in hospitals every single day. And we know because its mysterious absence in the universe is one of the deepest questions we can possibly ask. The story of antimatter is a testament to human curiosity. It shows us that the universe is far stranger and more wonderful than we could ever imagine from our everyday experience. It began as a ghost in an equation, a mathematical quirk that seemed too odd to be true. But we followed the clues, built the machines, and found the evidence. The mirror world is real. It's a part of our universe, a silent partner to every star, every planet, and every one of us. And the search to understand it, to understand why there is something rather than nothing, continues. It's a beautiful ongoing detective story, and we are all a part of it. Good night.